My apologies for a technical delay. Now the speakers from China are here. We anticipated their talk, and the first talk is a hybrid model based on adaptive active counter and multiscale attention for pearlite segmentation in metallographic images. There are 3 authors here, and the presenter, Jingwen Xiao, if I'm correct, but please, you're welcome.
Okay. Good morning, esteemed colleges, researchers, and attendees. My name is Jingwen Zhao, a doctoral student from Northeastern University of China. Since Jingwen Cong is unable to attend this conference, I'm here today to present her innovative research titled a hybrid model based on adaptive active counter and multi-scale attention for pearlite segmentation in metallographic images. Next, I will introduce the work in 5 parts, including background and motivations, related works, challenges and contributions, proposed method and dataset and experiments. Now, I will introduce the background and motivations of this work. Now, today, the world of materials science has long recognized the importance of microscopic analysis of high-temperature carbon steel, the analysis of the composition and the structure of high-temperature carbon steel, and the cast iron, particularly the distribution and the content of the pearlite, is crucial for understanding its mechanical properties and overall performance. In this study, we introduced a novel automatic segmentation method for pearlite segmentation in metallographic images, addressing the limitation of exciting neural network-based methods and overcoming the obstacles presented by metallographic image variations. In our work, we mainly focus on the following points: a multiscale attention-based U-net architecture is introduced as a backbone network. The second, adaptive active counter model with self-turning evolution parameters is incorporated in the backbone network. Thirdly, a new annotated metallographic dataset coded MHCSP is constructed. In this study of metallographic segmentation, many scholars has made contributions like Chen and Zhang et al. Despite their success in certain tasks, these algorithms predominantly focus on local or pixel-level attributes of the object, often disregarding its geometric properties. Such issues induce limitations in the precision and operational efficiency of the segmentation algorithms, frequently resulting in inability to accurately outline the boundary specifics of objects during identification. As an important algorithm in image segmentation, active counter model has produced a lot of important works. For example, Zhang and Hongji et al. Nevertheless, factors such as the consideration of pixel-level features, counter initialization, and evolutionary parameter settings affect the segmentation performance of the active counter algorithm to some extent. So there are some challenges should be faced. First, in pearlite segmentation tasks, one key challenge is the substantial variation in metallographic images, including difference in scale, texture, and illumination conditions. Due to their sensitive to such variations, neural network-based method may not be robust enough to cope effectively, leading to decreases the segmentation accuracy. Secondly, the structure of carbon steel containing pearlite is often different, so exciting methods may fail to deliver satisfactory performance, particularly when it comes to accurately capturing the intricate boundary details in pearlite segmentation tasks. Thirdly, the active counter models exhibit certain limitations that say choosing an optimal set of parameters for diverse images with varying characteristics is challenging, which can lead to suboptimal performance when applied to different image types without fine-tuning. Furthermore, the active counter model is sensitive to initial counter placement, which can result in inaccurate segmentation. Before formally introducing specific methods, let's take a look at the main contribution of this work as a whole. First, an automatic segmentation framework is proposed, which integrates an active counter model that can effectively handle the inherent complexity of metallographic images. Secondly, a multiscale attention mechanism is introduced, which can selectively focus on spatial and channel information at different scales. Thirdly, adaptive active counter model with self-turning evolution parameter is presented. Finally, a self-built metallographic dataset has been constructed. In detail, our methodology is arched in two primary innovations. The first is multiscale attention-based unit architecture. The other word is the backbone network. The second is adaptive active counter model. First, let us see the multiscale attention-based unit architecture. As we know, traditional unit architectures, while effective, often struggle to focus selectively on relevant features across different spatial scales. Our enhanced unit architecture introduced multiscale attention models. So through its structure, these models are strategically placed in both the encoder and the decoder parts, as well as in the skip connections and the bottleneck layer. What this achieves is a model that can discern and prioritize the most relevant spatial and channel-wise information at various scales. The attention mechanism ensures that the model captures a richer, more detailed understanding of the image, leading to a more non-state feature extraction and representation. Secondly, allow me introduce the adaptive active counter model. The world of image segmentation has long recognized the power of active counter models. However, their reliance on fixed evolution parameters often becomes their Achilles heel. Our approach introduced dynamism into this equation. The adaptive active counter model we have developed can adjust its evolution parameters based on the unique characteristics of each input image. This adaptively ensures that the segmentation is not just accurate but also tailored to the specific nuances of the image, eliminating the need for manual parameters tuning. The specific meaning of the parameters contained in the above adaptive equation are described below. So, by synergistically combining these two methodologies, we have crafted a hybrid segmentation framework. Here is how it operates. The process is initiated by the backbone network, which undergoes rigorous training using pixel-level annotations. This network then generates preliminary segmentation predictions. These predictions are then passed through the crucible of the adaptive active counter model, which refines and sharpens that segmentation. The end result is a segmentation output that mirrors precision with adaptively. Hybrid segmentation framework is shown as these pictures. To test the mettle of our approach, we constructed the MHCSP dataset. This dataset comprising 60 meticulously created metallographic images of high-temperature carbon steel, serves as the proving ground for our methodology. The diversity of images spanning both ferrite, pearlite, and modified light-braid structures ensured that our approach was rigorously evaluated across a spectrum of scanners. The specific results of the ferrite pearlite transformed the light-braid images experiments and sensitively experiments are shown on the following pages. That us can see from these pictures. This is the experimental result of our work. The experimental results show that our research marks a significant straight forward in the domain of metallographic images segmentation by harmoniously integrating the power of deep learning with the appreciation of classical methods. We have charted a pace towards segmentation that is both intuitive and accurate. There, I'd like to express my profound gratitude to my co-authors, collaborators, and the inter-team at the key laboratory of data analytics and optimization for smart industry for their relentless dedication and invaluable insights. This is the end of my report. If you have any questions and or interest in the content of the report, please connect the following email address. Thank you for your time and attention.
Thank you for your talk. I have some questions to you. The first question is, did I understand correctly that you used images of both cast iron and steels?
There, I should say something is that I'm not the author of this work because the author of this work is because since some things cannot attend this conference, so I just report her work. If you have some questions and or interest, you can connect the email address of the final page of the PowerPoint. Thank you.
Okay.